It is a great pleasure to start the academic content of the conference. And it's even a greater pleasure to start it with the Best Paper Award session. And I would like to invite Charlotte Lefebvre to present the paper by herself and Bart Manning, permutation-based hash chains with application to password hashing. Charlotte?
Thanks for the introduction. Can you hear me? No. Like this? Is it better? No. And like this? Okay. So indeed, thank you for the introduction. And this is indeed a joint work with Bart Manning, which is about permutation-based hash chains with applications to password hashing. So the very high-level motivation behind that work is second-factor authentication. So many systems rely on passwords for authentication, but we know that passwords are also quite a weak link on the chain as they are susceptible to many attacks. And this is why second factor has been introduced, because it adds an extra layer of security in order to mitigate the risk of passwords. So the second factor can take several forms. It can be biometrics. It can be a one-time password that is sent by mail, by SMS. It could be a hardware token, or also an application on your phone, like Microsoft Authenticator, that allows to generate these one-time codes. And some of them are based on time-based one-time passwords. So for example, this is the case of Microsoft Authenticator, where you have these 6-digit numbers, which allow you to generate one-time passwords. And under the hood, for example, Microsoft Authenticator, we have TOTP, which stands for time-based one-time password algorithm, and it was specified as an RFC. So its cryptographic core can be described as follows. We have a client, so typically a Microsoft Authenticator app, and a server, which is typically a web service. They first go through a registration phase where both agree on a secret key kappa. And then in the subsequent authentication rounds, what they are going to do is that the client will take this key kappa and a time-based counter, and they apply HMAC on this input. So the counter typically changes every 30 seconds so that a password is valid for a duration of 30 seconds. And then the output is truncated to a 6-digit number, among others, to make it user-friendly. And this code is sent to the server, which is going to perform the same computation in order to check that it coincides. One criticism that was made of TOTP is that here the security of this relies on the fact that the server must securely store a key kappa. And if you don't want the server to store any secrets, there exist actually some alternatives, and one of them is to use hash chains. So looking ahead, the scheme that we will be looking at is named Tiki, and Tiki is inspired from ASCII. So the ID dates back from 1981 with Lamport, and it was later specified as an RFC. But back then, second factor authentication was not a thing. So the goal of ASCII was rather to enhance the classical password-based authentication. So it works as follows. We have the client. So for example, your laptop. During the setup phase, it is going to generate a hash chain. So from the user's password and some salt, the element x0 here is going to be again, during the setup phase, the client is going to send securely the tip of the chain xk to the server, which is going to store it. And then if you want to authenticate at a later time, you can go 1 point backward of the chain and send here xk-1 to the server. And the server, when it receives it, is going to check whether the point that they receive is indeed a pre-image of what they store. And if this is the case, then the client is successfully authenticated. And you can apply this process in an iterative way. So intuitively, this is secure because if you have a good hash function, it must be pre-image resistant. So as an adversary, if you don't have access to the secrets, then it should be computationally infeasible to revert the hash chain. So once again, ASCII was rather to enhance password-based authentication. As such, you could use it for as a second factor authentication mechanism, but there were several criticisms that were made for FSE. The first one is that FSE is not time-based. So in other words, the time between two authentication runs could be days, months, or years, and therefore it increases the attack window for the adversary. I'm not going to go into the detail, but you might want to have something that is time-based on top of FSE. However, if you do it in a quite naive way, looking ahead, I will explain it in a slide, but you will need a hash chain which is very large. But on the other side, we know that if you iterate a hash function k times, then there is a security degradation by a factor of k. So that's why Tiki was introduced in 2007 by Kogan et al. And Tiki mitigates this multi-iteration problem by adding some domain separation into the hash function iterations. So in other words, now the hash function takes additionally a counter, a time-based counter, which is therefore different from any point on the chain. And if you have a random oracle, then you have independent hash functions. Moreover, here there is ID, which is a random salt, which makes it more robust against pre-processing attacks. And the goal of Tiki is to propose an alternative technology to TOTP, so as a second factor. And in that setting, we have therefore that X0 is a uniformly random string. And the one key feature of Tiki is that the passwords, so here the chaining values, they have a limited amount of validity. And they are valid for 30 seconds. So in other words, for example, let's say that I authenticate at a certain time and give X2, and I want to authenticate exactly 31 seconds later, then I should not give X1, go 1 point backward on the chain, but another point backward, so give X0 here. Which means that the more time is elapsed between two authentication rounds, the more you need to go backward on the chain. So this is the suggestion by the designer to instantiate the parameters. So S is the salt size, and they suggest to have 80 bits of salt, the counter over 32 bits, and K, so the length of the hash chain is suggested to be 2 to the power of 21. So this is a very large number, and they chose this number because they wanted a hash chain to be valid for 2 years. And this is where you can see that this is so important to have domain separation, because if you didn't do so, then there would be a security degradation of 21 bits here. N is the salt of the passwords, and they said 130 bits, and 30-second time frame. So the designers of Tiki, they prove a security of their scheme. If you assume that H is a random oracle, then Tiki is secure up to 2 to the n random oracle queries. However, when we looked at the security model of Tiki, we noticed that the time-based release pattern of Tiki, the fact that you have passwords valid only for 30 seconds, and other things, that could be further better captured in the security model. But I will go into more details in the next slide to explain the differences. But in a nutshell, we refine the security model with more fine-grained adversarial metrics. And then we redid the security proof in the new model, and we proved, therefore, a better bond that leverages the source and the offline and online phase. And then we were interested to have a look at the security guarantees of Tiki if you instantiate the random oracle with a hash function construction. So first with a sponge construction based on a random permutation, and then a truncated permutation. So about the security model, so here H is a hash function based on an ideal primitive P, and the game has two different phases. We have first an offline phase where the adversary has only oracle access to the ideal primitive, and it has a number of queries equal to Q-off. And typically, Q-off is going to be the largest number of queries that the adversary can do. And we will typically aim for 128 bits of security in the offline phase. And after the offline phase, we have the online phase that starts. And at this point, the adversary is given the salt and the tip of the chain xk. And it has a limited amount of queries, Q on K, in order to try to provide the preimage of xk. And typically, we want to choose Q on K in such a way that it captures the fact that the adversary has only 30 seconds to try to invert xk. And if during that queries, the adversary did not manage to find a preimage of xk, we go 1 point backward in the chain. We give xk minus 1, and this time the adversary needs to invert xk minus 1. And again, it has a limited amount of queries, and so on, and so on. And the adversary wins if they manage to provide a preimage of any point on the chain during their lifespan. So the difference between the security model and the one of Tiki's designer is that in their setting, the adversary could choose freely how they spend their query budget. So for example, the adversary could just say, yeah, I don't want an offline phase, and I'm going to spend all of my queries trying to invert xk. But this is not realistic because in real life, you have potentially a larger offline phase with much more computational power, and you have only 30 seconds to invert 1 point. So we denote the security advantage by this quantity. Yeah, this one. So there, Q on is the sum of all of the online queries for the adversary. So this is for simplicity that we gather them together. But in real life, like in the security proof, we actually consider this separation. And in order to leverage the sorts, we also consider the multi-user setting, where we have M users. And yeah, so for Q on, we made some computation in order to estimate what upper bound would be reasonable for the online phase. And we ended up with 100. We ended up with the conclusion that 100 bits of security is a reasonable upper bound. You can check the papers in order to get more details. Okay, so our security model is a strict generalization of the one of Kogan et al. So we can we can see what security bonds do they have. And in their setting, as I said, they did not make a distinction between online and offline phase. Therefore, we have this security bond. And on the other side, we proved the following security bond, where intuitively we made use of the fact that during the offline phase, the adversary is not given the salt. So if the adversary is not given the salt during the offline phase, it needs to do more work. It needs to guess the salt in order to make them useful. So if the number of users is not too high, then there is the penalty during the offline phase of this factor. And during the online phase, well, basically it doesn't change. And yeah, so if we target this 128 bits of security during offline phase, 100 bits of security in the online phase, and we assume that the number of users is not too high, then this security bond tells us that generically you can lower the password size from 130 to 100 bits, which can be quite interesting, especially if you're in the scenario where we want to minimize the amount of data that the client transmits to the server. So that was Tiki security model and random oracle results, but we might wonder what's happening if we instantiate Tiki with a hash function construction. So actually the security game that we have is one is a single stage game. So you can actually compose with indifferentiability this way. And the rightmost term corresponds to indifferentiability advantage of the hash function construction. However, we think that indifferentiability is overkill in that setting because, well, indifferentiability is a very general security notion. So in particular, indifferentiability doesn't really care if you're considering a number of offline queries, a number of offline query. They are all it is actually a complex variant of preimage resistance. And we know that in many settings, we have actually better security bonds than indifferentiability. So this motivated us to have a look at a dedicated analysis because we thought that we would get a better bound. So we first started to have a look at Tiki with the sponge construction. So you're probably already familiar with the sponge construction, but at least to give some notation here, let me redescribe it. So the sponge construction is a permutation-based construction in order to provide an extendable output function. It operates on the state of size of the same size than the permutation, so b bits. And this state is split in two parts. We have the outer part at the top of size r bits. R is also called the rate. And at the bottom, we have the inner parts of c bits, and c is called the capacity. And then in order to process a message. This message is first injectively padded. So typically the 1-0 has padding. And the padded message is split into blocks of orbits. And these blocks, they are added one by one to the outer part of the state. And this is interleaved with permutation evaluations. And after processing all message blocks, then the digest is also extracted by blocks of orbits. So it was clear from the start that the sponge construction has a tight indifferentiability bound up to the birthday bound in the capacity. So maybe to have a bit of a more graphical representation of what's happening when you use sticky with sponge construction, it can be represented as follows. So we start from a random password x0. And then we pad this random x0. We can do this because it's the 1-0 as padding. And the padded message is plugged into an instance of the sponge construction with the salt and the first counter. The blocks, they are added and absorbed, and then the digest is extracted, and we obtain, therefore, the one chaining value. Well, you need actually to truncate it in order to get the next password. And you can pad it again in order to plug it into the second instance of the sponge with the second salt and counter instance. You squeeze again, and then you truncate again, etc., etc. So this is how you obtain this hash chain with the sponge construction. So actually, so here we have that the salt and the counter, they are absorbed by blocks of orbits. But looking ahead, in the security proof that we had, there is no difference between absorbing the salt and the counter by blocks of orbits or directly initializing the inner part of the sponge with the salt and the counter this way. So strictly seen in this setting, you kind of randomize the sponge state before you absorb, while here, well, they are fixed. But for us, it didn't change anything. And if you do things this way, then you can be a bit more efficient. So the security bond that we have, they hold both for the sponge and this optimization. So, okay, so about the security of Tiki with the sponge construction, if we use generic composition with indifferentiability, we obtain the following bond. With this term, that's, well, birthday bond in the capacity with the offline complexity. So among others, this tells you that if you want to use Tiki with a sponge based on a permutation, then you need that your permutation size is at least 256. Well, actually, this is the capacity. This is 256 of capacity plus at least 1 for the rate. So for most applications, this is completely fine, but we were wondering if this is actually possible to reduce the minimal size of the capacity in order to have a secure instance. And we derived a dedicated bond for that with this. So here, the birthday bond in the capacity transform into a linear term, although with a factor loss of k. So we kind of lose 21 bits of security. But it means that then you can lower the capacity to 149. So the rightmost term here, I'm going back to this one in the next slide. And we have this leftmost term, which is annoying in the sense that if you think about it, like the whole point behind Tiki and this domain separation was actually to get rid of this term. But here in the security bond, it comes back. And this is not a mere artifact of our security proof, because actually, if this is easy to find in a collision in the sponge during the online phase, then you can actually find an attack with this success probability. So on one side, this bond tells you that the password size needs to be increased, but you can reduce the size of the capacity. So for example, if you consider the size of the permutation of spongent, then you can use it in a Tiki instance with sufficient generic security. So a few words about the security proof. I'm not going to dive too much into the details, but at least give the high-level intuition. So actually, in the security proof, we had to split the probability computation into several pieces. And we ended up with k instances where the adversary needed to find a preimage for one single call of the sponge construction. And actually, it corresponds to everywhere preimage resistance of the sponge, where 3 years ago, we proved this security bond, the following security bond, which is tight. So we could reuse these results but we had to work a little bit more on the bad events because here we have Tiki with the release pattern. So we needed to adapt a little bit the proof in order to adapt to the online and the offline phase. And actually, the tool that we used in order to split the probability computation, we used the PRF security of the AutoKit sponge. So the AutoKit sponge, roughly, it's about taking the key, the message input, and feed it into the sponge construction. And here, in the case of Tiki, you can actually view the passwords or the chaining values as the key of the AutoKit sponge. So what I'm saying is probably a bit vague. So maybe with a graphical illustration, it will be a little bit clearer. So if you think about the security game underlying Tiki, it is actually, we have actually k different security games which are overlapping between them. And each security game is about finding a pre-image of a chaining value. So in the first game, the adversary wins if they find a pre-image of x1. We have actually a random password x0, apply it into the sponge, and we get x1. So it actually corresponds to so-called domain-oriented pre-image resistance of the sponge. The second game is about finding a pre-image of x2. So again, we have online and offline phase, but with complexities shifted by 1 unit. But actually, we have x2 that was generated from x1, which was itself generated from x0. But x1 also comes from an AutoKit sponge call, which has a PRF advantage. So we can actually replace x1 with a random value. And in that setting, we end up with a game which has exactly the same form as the game before, so domain-oriented pre-image resistance of the sponge. And you can actually repeat this reasoning in an inductive way so that you can get rid of the cascading nature of sponge evaluations. So we are not done yet. We need to do a little bit more of work to transform this domain-oriented pre-image resistance into everywhere pre-image resistance. And I won't go into the details, but you can actually use, again, the PRF advantage in order to end up with those instances. So that was the sponge construction. But OK, so this is the optimization that we had. But if you think about it, for most permutation sizes, it's actually enough to do only one permutation call to absorb everything. If the size of the rate is large enough, then the whole password gets absorbed in one permutation call. And in that case, what we obtain is a truncated permutation. And yeah, the hash chain becomes a truncated permutation chain. So again, same story. We might wonder what security bond do we get if we use generic composition with indifferentiability. So the two rightmost term here, it's indifferentiability of truncated permutation. So the indifferentiability advantage depends on the size of the fixed prefix and the number of bits that you truncate. But yeah, I won't go into the details. And this is the security bond that we obtain. So we have advantage of Tiki with a random oracle, and we know that this bond is tight. And here we have some extra terms. And these extra terms, they come from the fact that the underlying primitive is invertible. So in particular, this is bad if the adversary is able to, via an inverse permutation call, guess one of these states. But we had to deal with the online and the offline phase and also with multi-collision. And this is why we get these two extra terms. On the bright side, the bond that we obtain is tight. So you can find a matching attack. And well, a bit more concretely, let us assume that this time we really want the password size to be of 100 because we know that generically this is the minimum password size you can obtain. And we make this assumption on online and offline complexity. Then for generic composition, this is generic composition in the single user setting. It tells us that we would need to have permutation size of at least 260 bits. On the other side, our security bonds tells us that you can go as low as 200 bit permutations, as long as the number of users is not ridiculously high. So to conclude, in this talk, we analyze the security of hash chain-based password systems. So our result, they apply mostly to Tiki, because you have in Tiki this release pattern that's unique to hash chains. But what we did is to have a refined security model that distinguished the online and the offline complexity. And this came with security proof, with a random oracle, sponge, and truncated permutation. And actually, for most cases, as soon as your permutation size is 200 bits, then it's better to use truncated permutation. And in that setting, it is possible to have a password size as low as 100 bits. For the sponge, the result that we have, they also allow to increase the applicability. But admittedly, this result is a bit more theoretical. It actually allows us to understand a bit better what's the pre-image resistance of the sponge when you have cascaded evaluations. And of course, all of the results here, they hold in the random oracle or random permutation model. So that's it, and thank you very much for your attention. Yeah, thanks for the question. I'm just thinking that's quite interesting. So if you continue the hash function, maybe I'm not seeing.
So instead of like in any other mode where you just you put some stuff in, you get some stuff out, you put some things again, because this seems like a natural extension. Have you looked at something like that, or what is your intuition about something like that?
Yeah, I think this is quite a great idea. I haven't thought about it, maybe Bart did, I don't know. But that seems, yeah, I'm thinking whether it will cause problems, because it's also nice because you can also store the state. And then maybe you can go backward if you do that. So yeah, that seems, I need to think about it. Thanks for the question.
Are there any other questions? If not, let's thank the speaker again.
Okay, now we have the coffee break, and he's going to be in the next room, so the room after, next to this one.